Hey folks, good afternoon, thanks for coming. Today we're going to talk about some work we've done at Airbnb on GraphQL execution. I work on a project called Viaduct. It's basically a very fancy GraphQL server. I'm not going to go through the whole Viaduct backstory. In fact, Adam, put up your hand. He's talking at 5, and he'll give some more information. I want to start actually on the bottom bullet point here, which is to say, hey, we have designed Viaduct from the start to support what we call decentralized development of large central schemas. And I think if you look at these numbers, it seems like we've been successful there. We have over 130 teams working, contributing to the schema, so that's very decentralized, and it's a large schema. So we have been at this for over 5 years. For most of those 5, it's I guess going on 6 years at this point. For most of that time, it's been a very bottom-up, you might say, responsive in terms of working with clients. Sometimes perhaps reactionary, where people come and say, "Oh, how do we do this?" And we kind of invent stuff on the fly. And the net of it is that Viaduct got into a place where we had learned a lot along the way. But the code base itself had layers and layers and layers of experiments kind of just left behind. So almost 2 years ago, we started a new project, Viaduct Modern, we call it, because we don't like 2.0. That's too old-fashioned. So we have a new approach, or a new thing, where we've tried to take all of the lessons we've learned and put it into a nice new package. One thing to be aware of is that sometime in the next week or two, we're actually going to be open sourcing the modern version of Viaduct, so you'll all get a chance to kind of play with what we're going to talk about this week. But anyhow, I'm going to talk about the engine. There's actually 2 layers to Viaduct. There's an engine and then a developer-facing API. I'm going to focus a lot on what we call re-entrancy. And so let me explain kind of the context for that concept. So again, we want to support decentralized development of a large central schema. This might be seen as a euphemism for a monolith. And in fact, we do take a monolithic approach to what we do. The team has had a lot of experiences, good and bad, with monoliths. And with respect to what we view to be kind of the major pitfall of monoliths, it's lack of modularity. Monoliths become a problem when people reach into other people's code in uncontrolled ways, and before you know it, anytime you try to change your code, you break stuff you didn't even know existed. And so from the start, we wanted to get a strong sense of modularity into Viaduct. And so we created, kind of evolved this notion of what we call re-entrancy, which is to say, the graph itself, GraphQL, is the mechanism by which the different teams, the different modules can interact with each other. So even though we run most of the code in a single process, the different modules can't call into other people's code. They have to interact through the graph. And I'm going to illustrate that. So I'm going to use this running example, very kind of classic simple schema. The main part of it is in the upper right corner, where we have a user type, which implements a node, a bunch of fields there, a couple of query things that we'll take advantage of. But on the user side, part of the way Viaduct works is we have a concept of a node resolver. So for every type that implements node, as a developer, you have to provide a node resolver that goes with it. The node resolver is responsible for, obviously materializing the fields of a node, but not all of them. And so in the example, you can see 2 fields, full name and climate, that are marked with @resolver, and that indicates that those fields have dedicated field resolvers. And so the important thing to keep in mind as we go through this example is that the node resolver has to return first name, last name, and zip. And then there's 2 dedicated resolvers for full name and client. Another thing to note about Viaduct is it takes a schema-first approach. So that means that developers write schema like this. They check it in. And then we have a build process that generates all kinds of convenience functions to make it easier and more type-safe to develop your code. And so, let's see. All right. Oh, let me make sure it wasn't buffered. OK. So here's an example of some code that illustrates some of these generated types. And so for each field that's marked with @resolver, we generate what we call a resolver base class. And so you see user resolvers.fullname is the base class for the full name resolver, and user resolvers.climate for the climate resolver. And so as a developer, you just subclass the appropriate base class, override resolve, provide your code, off to the races. This approach to having a class that you implement actually gives us a very convenient place to kind of do injection of dependencies. So every time the resolve function is called, a new instance of this class is created, you can inject whatever you want into it, and that makes it very good. So now let's talk about reentrancy. And there's two kinds of reentrancy that we have. Both are illustrated here. One is subquery reentrancy. So a resolver can just simply make a query. In this case, to get the climate of a user, we're going to take their zip code, call climate by zip, get that climate, and return it. So this has proven to be a very useful form of reentrancy. It's used a lot across our code base. But that's not what I'm going to focus on today. Instead, I want to focus on a different kind of reentrancy, which uses what we call required selection sets. So in the two resolvers illustrated here, the full name 1 needs the first name and the last name of the user to return the full name. And in the case of the climate one, it needs the zip code in order to get the climate by zip. And so we call these required selection sets because they basically express the data that's required by the resolver in order for it to run. And so if you've heard VIDA talks in the past, you might have heard us talk about what we call derived field providers, and perhaps in this talk I'm going to slip and call it a DFP. These things are DFPs, and this form of reentrancy we've had for a long time, and again, has proven to be quite valuable. Oops, I guess I got a point over here. Okay, so more quick history. So the original implementation of this form of reentrancy was kind of clever. For every place where there was an @resolver, we kind of created, in the root query type, a shadow entry, which we could run a query against to kind of get the results for that particular fragment. So essentially what we did is we took this RSS reentrancy and turned it into subquery reentrancy. And that worked, but it turns out it's kind of a pain to maintain. But it has an additional problem, which is the same resolver gets run over and over and over again. Later on, I'll kind of show you why that's the case. But that leads to what we call query amplification, where one query from a client can turn into many tens of queries kind of internally to satisfy these. One nice thing about that previous approach is that we didn't have to change. We used GraphQL Java to, underneath the covers for Viaduct, and we didn't have to change the execution at all. So as we said, hey, we got to kind of get to a better approach here. We kind of went down this abandoned path of saying, hey, let's rewrite queries, right? So we're going to take the input query, where we see a field that has a required selection set. We're going to kind of insert that into the query, right? And so we're going to rewrite the query with all this other stuff inserted into it. And then again, the benefit of that is we can then just feed that, to an existing execution engine, and it's all good. It turns out that between aliases and argument values and skip and include, that rewrite becomes a nightmare of bookkeeping. And so, where we were hoping to make things simpler, in fact, it was just getting more and more complicated. And so we abandoned that, and we abandoned the hope of saying, hey, look, let's do this without changing the execution strategy. And so we have changed the execution strategy. I'm going to walk through the new strategy. And there's, oops. I'm going to have to stay over here. There we go. Three main concepts that will come through here, which is resolution keys, memoization, and query plans. So, okay. Hello, there we go. All right. So, first of all, with respect to the new execution strategy, we've actually broken it up into two separate phases. There's a resolution phase followed by a completion phase. We're going to, again, in the talk today, we're going to talk mostly about the resolution phase. In the resolution phase, we kind of build up what you might call a normalized tree of what the engine is being asked to produce. And we call this an object engine result tree. We have a special kind of key, for the fields of that tree called resolution keys, and that allows us to kind of build up, a tree. Once that tree is built up, we have a completion phase where we take the result keys in terms of what the end client wants the fields to be called, and we kind of populate the result tree. And we do a whole bunch of other stuff like dealing with nulls and coercions and so forth. It's in that first phase that we call execute resolvers, what a lot of people call data fetchers. In the second phase, everything just gets read out of the tree generated in the first phase. So here's the first, arguably interesting thing in the talk, which is these things called resolution keys. Typically when you think of an object in GraphQL, in an implementation of GraphQL, right? It's like map of string to value, right? And that string might be the field name, it might be the alias, but there's this tendency to think of it as string to value. We've generalized the key for the first phase resolution, where it's not a string, it's this triple where it's the alias, it's the field name, and it's the value of all of the arguments, right? So all of that is the resolution key. And we would argue that creates, if you will, a unique coordinate for a result. And so this kind of solved that bookkeeping problem that I mentioned with the query rewriting, right? We don't have to guess, and make up names for stuff. We have a well-defined coordinate to put results. So we have this key. Other than that, right, the object engine result tree is a tree, right? We've got, it's got keys, it's got values. Here's an example tree. So I'm going to walk through the construction of such a tree, during query execution. And I'm going to omit the alias part just to make the slides a bit more readable. So that's okay. So we start query execution with the object engine result for the root query. The next thing is we see this node. The node has an ID. It's a particular value at runtime. In Viaduct, and this came up in one of the sessions before, but in Viaduct, the type of a node is embedded in the ID itself. So when we get an ID, we know, oh, this is an ID for a user. So we can, as it's shown on the slide, create an object result for user type. And in fact, we can populate the ID field for that type. So at this point, remember I said there's a node resolver for user. So at this point, we're going to kick off that node resolver. It's happily running in the background. But full name also has a field resolver. So why wait, right? We kick off the field resolver for full name, totally in parallel. And so I'll probably just stay over here. So now full name, the first thing it's going to do is say, hey, I need first name, right? You saw the code. It's going to ask for first name. First name isn't available. So part of what we do in our engine is we wait, right? So basically, this is all Kotlin, so the full name resolver is going to suspend, waiting for full name to result. And again, I think it's a little bit subtle, but this illustrates the value of having this kind of coordinate space for values. The implementation of full name just has to know, hey, here's my OAR key. Like, please go get me this OAR key. It can ask for it. It doesn't have to know that that comes from the node resolver. There's no dependency tracking that comes up. It's all implicit, through these OAR keys. So full name is waiting. Now here's another thing that's subtle. The node resolver, the question, if you're the node resolver, is, hey, what field should I return? Right, so one of the goals of GraphQL is to allow, selective fetching. And so if you look at the query on the right-hand side, first name and last name aren't mentioned. And so somehow we have to tell the node resolver that it needs to get these other two fields as well. That's where query plans come up. And we'll talk about query plans briefly. But trust me, the query plan will take care of that, which means the node resolver returns the first and last name, which means the full name gets unblocked. It does its job. At this point, resolution is finished. We finished with the first pass of our query execution. And again, this whole approach of just saying, hey, I want this field, and you wait for it, has really simplified kind of all the synchronization logic in our system. Field completion then just kind of runs through this stuff and says, hey, what are the fields I actually have to return? And if there's aliases, apply them. And we generate the response tree. And that's the second phase. All right, so let's talk about query plans. So to make the conversation about query plans more interesting, I've going to add a new field, display name. Display name depends on full name, and then full name depends on first name and last name, so we have a nice kind of transitivity here. Okay, so here's a query. I made this up weeks ago, but apparently fragments are all the rage, this conference, and I put a fragment in, so a fairly standard query that you would get. So let's come up with a query plan for this query. And so this is the top level plan. This is kind of the start of a plan. So this is a query plan. And notice that we've done a little bit of field merging here, where we took the two full names and kind of merged them up. But there's only so much merging that you can do, because query planning, just to be clear, query planning kind of happens once up front when, say, your persisted query is kind of put into the cache, we plan it, we kind of cache the plan with it. And at that point in time, there's a lot of stuff you don't know, and therefore you can only go so far. And so in particular, there's constraints or conditions on fields, that are naturally kind of part of GraphQL. There's type conditions, so for example, if the ID comes in here and it's not for a user, none of these fields will show up, right? So that's a condition. There's also skip and include are additional conditions. And so kind of dealing with those conditions is kind of a pain, and it does limit how much merging you can do up front. So this still, at this point, we haven't answered the question, hey, how does the node resolver know that it has to get the first and last name? And so this is where child plans come into the equation. So we have these things called child plans. And what they do is they basically take the required selection sets of fields, and they just kind of stick them in as child plans. And so each of these child plans is a full-blown query plan, right? So this is a recursive data structure. As you can see, there's conditions in there and so forth. And then, this kind of happens iteratively, until you bottom out. And so child plans can have child plans. In this case, under display name, there is 2 layers of child plans. And so now we're in a position to answer the question, how does the resolver for the user type know what to do? So at execution time, we do have everything we need to kind of deal with these constraints, decide what is or isn't in place. At that point, we can do kind of a final merging of fields, including and especially fields from the child plans, and that's the selection set that we give to the node resolver, and that's how it knows that it has to get first name and last name. So just to summarize, it's through the child plans that we capture these RSS reentrant elements. And I wanted to get back to this whole query amplification kind of thing, because it's easier to kind of explain it here. Notice that full name shows up twice in that query plan. And in fact, in our original approach to the implementation where those things happen through a subquery call, full name will get called twice, right? And so you can kind of see how that could very quickly get to the issue of lots and lots and lots of subqueries getting called. And so again, I think that this idea of an OER key, giving us a unique place to put values, right, so that we can memorize them and not kind of call them on the fly because we don't have a place to put them, is great. And it's led to what we call kind of the single writer, multiple reader approach to stuff, where for every field there's a coroutine that's responsible for writing it. There's all kinds of other coroutines, in a loosely coupled way, can kind of subscribe to read it. And so that's the summary. We have, again, given the numbers I've shown you, I think proven support for the centralized development of a large central schema. It's our view that reentrancy has been key to allowing us to support so many developers in a single code base. To support this, we have a new execution strategy with OER keys and query plans as kind of being the heart and soul of that. I'm going to actually flash this up without going into any details. If people are curious about any one of these, you can ask. But going back to the open source thing, when we do open source Viaduct Modern, I like to think of Viaduct Modern as new software with an old soul, right? Old soul meaning we've been at this for almost 6 years. There's a lot of experience that has gone into it, but the code base we're putting out there is brand new. And I think that we're doing this, we're putting it out kind of this early because we want to encourage people to participate, right? And so here's some of our ideas, but there's other ideas. And would love to have people join up and kind of help influence the software while it's still relatively young. One more quick pitch. You notice it says query plans to guide batching. We actually have, I think, a very clever idea of how to deal with the n+1 problem. So Eileen, put up your hands. On Wednesday, we're going to talk about that. And so you can connect it back to this talk in terms of how, that API and, this planning process can fit together. So I did want to leave some time for questions.
So, the examples you showed in Node.js are in JavaScript.
It was Kotlin, but yeah.
So when you're writing the result, you're actually writing the result.
Yes, but we have aspirations actually to be a polyglot system. And so because we have this very loose coupling between the engine and that resolver code that you saw, it could be any language, right? As long as it can kind of read and write into these OER fields, it's good to go. And so,
Do you have product developers? I'm a front-end person using these resolvers to create basically a view model-esque result that and pushing it into the schema, or is it mostly server
yeah, we could give a whole talk on that. The schema governance, we kind of put that under this big bucket of schema governance. I can't say we've cracked the code. We actually had a whole exercise of kind of MVC-ish stuff, which did not work out well, and we've kind of undid it. And I think we're still trying to find, we want a system where both back-end and front-end developers can come together in one place, and that's why this kind of multi-language thing, it's not theoretical. We really, mostly want to get JavaScript in there so we can kind of support both sides. It's not generated at compile time. I mean, it could be if we could put it into our persisted kind of query system and kind of have it available, and perhaps we should. I think the current implementation generates it a first time on the fly, caches it, and then reuses it subsequently.
How did you avoid writing on the fly
Yeah. There's, it happened, so that gets checked twice. So at build time, we actually will pull that text out and validate it using just standard GraphQL validation. And then at runtime, well, I shouldn't say at runtime, at server startup time, we go through all the resolvers and we check again because you just can't get that wrong. One of the most important checks, by the way, is everyone wondering, like, what do you do about cycles? Could this thing kind of get hung? And yes, it absolutely can get hung. And so one of the things we absolutely, in addition to just the pure GraphQL validation, we have to make sure there's no cycles in these things, or else bad things happen. More questions in 45 seconds? Yeah. What, the embedded ones? Yes, it's the same one. So the whole idea is we basically expand the query. Instead of expanding it up front at this kind of query rewrite time, we expand it actually during query execution. But it's, yes, absolutely in the same server. Yeah. Not yet. I will say 2 of those optimizations up there are in the interest of reducing the memory footprint of the query plans. So it's a concern. I'm going to take speaker's prerogative because I want to talk about my favorite optimization, which I call the next hop caching. So we got n+1 solved, right, with data loaders. But here's the complaint we get. At Airbnb, we have a listing. A listing has a host. In order to get the host data in a query, I have to load the listing, get the ID for the host, and in a separate hop, get the thing, and can't you do something and make that faster? And so I absolutely think we should, and this is not just for Viaduct, anybody could do this, but that's what I call the next hop cache, where we basically take the node ID of the listing, the host field, and we actually cache that. And it turns out that the host ID is immutable or as close to immutable as you can get. And so, that's a very durable cache. And I think, after you've solved the n+1 problem in terms of, hey, do I really have to wait for that? I think this is the next frontier. That's an excellent question, and in fact, it's a bit debatable, right? So one of the questions is, if I ask for the same field, in just an obvious way, the same field, same arguments, different aliases, what does the spec really say about executing it? Does it say it should be executed twice? One could interpret it that way, or does it say, hey, look, it's idempotent, and therefore, it doesn't say functional, it says idempotent, right? And that's a slightly different word. And so some people think we should execute it twice, in which case you need to put it in. Other people say you don't have to execute it twice, in which case you get rid of it. Yeah, yes, absolutely. I think, again, a point of disagreement. I think with mutations, you just kind of run through the query. You don't go through all this stuff for mutations. You just kind of run top to bottom, run them. And this is purely for the query side, if you ask me. Not everyone agrees with that. All right. I'm around, so if you've got more questions, happy to answer. Thanks.